Right. Hello, everyone. I'm Shashank Agrawal. I am a research manager at Coinbase and also a research partner for Delegation Ventures. Today, the panel topic is on the frontiers of zkMPC. We have several interesting talks that are at the intersection of zero knowledge and MPC. We also have a talk on FHE. Next slide, please. We have a fantastic set of speakers for you today. We have Alex Ozdemir from Stanford University. We have Pratyush Mishra from UPenn. We have Elette Boyle from IDC, Herzliya, and we have Rand Hindi from Zama. The format of the panel, next slide please, is going to be the same as before. We'll first have the speakers present one by one. Each speaker would have about 15 to 20 minutes for the presentation, and next we'll have the discussion panel, depending on how much time we have left, typically 15-20 minutes. And finally, if you have a bit more time, we can go into a bit more Q&A. You can also, if you have questions along the way, you can post them here or on the Telegram group. And if we have time at the end of a talk, we could also take them then. And if we have some time left at the end of the session, we can answer some questions at that time. Yeah. So let's get started. The first talk is by Alex, who is a PhD researcher at Stanford University. He'll talk about collaborative zkSNARKs. Alex.
Yes, thank you. Let me take a moment to set up. Okay, Shashank, can you see the screen share?
Yes.
Okay, awesome. Then yeah, thanks for having me here. I guess today's symposium is about the future of combinations of zero knowledge and MPC, or relationships between them. And so I'm going to give one specific take on that, and the other speakers are going to present slightly different takes. Of course, often there is a relationship, and that is interesting to see. So what I'm going to tell you about is a new primitive that we've defined that lives at the intersection of these two families of protocols. We call this primitive a collaborative zkSNARK. And the idea is that it supports a kind of zero knowledge proof about secret information that is distributed among different parties. And this is interesting because traditionally we think of zero knowledge as being something that applies to a single party's secrets. The example I always give is authentication. In an authentication protocol, there is a client and a server, and the client seeks to prove that it knows some secret information, a secret key, a password that only it should have. And it uses some protocol to accomplish this task. During this protocol, it's really important that the client, while it needs to show that it has this secret information, it shouldn't reveal the information itself, because if it were to reveal the secret information, then in the future, the server could impersonate it. And so some notion of zero knowledge here is necessary in order to build a secure authentication protocol. And indeed, general purpose zero knowledge proof tools like zkSNARKs, they can be part of the solution, part of the way that you go about building a secure authentication protocol. They're sufficient in this way, but they're not necessary. Of course, there are more streamlined authentication protocols. So traditional zero knowledge tools apply in situations like authentication, where the secret is localized, but there are lots of situations where the secret is not localized. And I'll just give you one example that we were thinking of while doing this work. We were imagining a money laundering scenario where there is an entity, Colonial Pipeline. There's an entity, Eve. Colonial Pipeline has paid a ransom. Eve has obtained that ransom via a sequence of transactions. And there are a collection of banks shown here with different colors that have witnessed this event. They have seen the sequence of transactions that move the ransom from Colonial Pipeline's custody to Eve's custody. And these banks would like to prove that this event has happened, that this transfer has happened. But the challenge here is that the global transaction graph, the graph in which all of these edges are visible, is not actually public information. Different entities, different banks, different individuals are aware of different edges. And so to show that this path exists, you need to show a property of secret information that is distributed among many parties, in this case, the different parties of the banks. And in this latter scenario, the traditional zero knowledge tools seem less applicable because the secret information is distributed. There are other natural situations in which secret information is distributed. Pratyush is going to talk about one, a setting where you where maybe the information is not necessarily initially distributed, but some client who wants to write a standard zero knowledge proof might distribute its secrets among other servers so that the servers can help it write the proof. So this is some kind of delegation, and I won't say any more about it right now because Pratyush will cover it in great detail. But one way or another, whether the information is initially distributed or whether it becomes distributed, secret information can often end up being distributed. And the question is, can you write a zero knowledge proof about it? And so I'll tell you about a primitive, a collaborative zkSNARK that is designed to do just this. We'll start with a few notes about its definition. I'll say a few words about how we constructed collaborative zkSNARKs, how we implemented them, and how they perform. And then finally, I'll spend a reasonable amount of the time discussing future directions, where we think this work falls short and what we think should be done in the future. And so the sort of distribution of time here is going to be more in favor of future directions, because I think that's probably what's most exciting. So let's get into it. Definition of collaborative zkSNARKs. It turns out that the definition syntactically is very natural. In a conventional zkSNARK, in the standard setting, there's a prover, there's a verifier, and the prover has a secret, W, and constructs a proof, pi sub W, that shows a fact about W. It shows that some predicate phi holds on the public data X and the secret data W. This is the standard setup. And in the collaborative setting, only one thing really is going to change. Instead of one prover, there are going to be multiple provers. So we imagine that there exists a sequence of provers, in this picture, 3 of them. Each prover has the public information, X, but each prover has a different piece of secret information, W1 through W3. The idea is that the provers are allowed to interact with one another. So they run some kind of interactive protocol, but this protocol outputs a single non-interactively verifiable proof that here I've labeled pi sub vector W. And the reason that I've labeled it that way is that this proof now is going to establish a fact about the vector of witnesses. It's going to prove a joint property of the secret information. So note, while the proving process here has become some kind of interactive protocol, and indeed our syntax shows that, the verification process is still non-interactive. It's just an algorithm. So the proving process, while interactive, produces a non-interactively verifiable proof, which we think is useful in a lot of settings. Okay, so this is the syntax. So this is what a collaborative zkSNARK looks like. Really, the only thing that's changed is proving. It's no longer an algorithm. Now it's an interactive protocol. What about the security? Security also has to change a bit. And I won't go through all of the security definitions that we have to write down for this primitive, but I'll touch upon one of the most interesting ones, which is the notion of zero knowledge. The reason that zero knowledge is interesting is traditionally, in a conventional zkSNARK, you have to worry about the verifier learning information that you don't want it to. But now, in a collaborative setting, you also have to worry about other provers learning information that you don't want them to. To give you a sense of the kind of leakage that we're worried about, imagine that there are 5 provers. They're engaging in this protocol to write a collaborative zkSNARK, and there's some adversary who has corrupted the first 3. Provers 4 and 5 might wish for a guarantee that says that despite the fact that there's some adversary who has corrupted some of their peers, that adversary is not going to learn anything about their secrets. So this adversary isn't going to learn additional information about W4 and W5, the witnesses of the honest provers. And ultimately, you can't quite achieve this. What we're ultimately able to define is a property that shows that an adversary who controls at most T provers learns nothing beyond whether or not the witnesses are collectively valid. And in some sense, it's going to be unavoidable to leak this, we call it a validity bit, because the whole point of the system is to build a proof that the witnesses are valid. This is leaked by design. But it does have some implications. It means that you shouldn't try to write lots and lots of proofs with a particular collection of people. If the proof keeps on failing, they might still be learning something. Okay, so the other thing to note about this definition is that it's a threshold definition. So this is a privacy property that holds as long as the adversary has not corrupted too many of the other provers. And we're going to achieve this definition for varying levels of T. Sometimes T is going to be half of the other provers. Sometimes zero knowledge will hold even if the adversary has corrupted all of the provers but yourself. It kind of depends on the construction. How do we actually formalize this? We do it in the style of MPC security definitions, focused on just the proving process. So we imagine an adversary who's constructed at least 2 provers. We imagine that the adversary might behave arbitrarily. They're going to deviate from the protocol. They're going to do whatever they can to get extra information. And we require that there exists a simulator who can simulate, who can fake the view of that adversary, given only access to information that the adversary has already, the corrupt witnesses in the public data, as well as this validity bit that I said that we were going to leak. Ultimately, we instantiate our definitions in the explicitly programmable random oracle model, and we do our analysis in that model as well. So there are some other facets of security that are a bit interesting, but for the interest of time, I'm going to skip them for today. And what I want to move on to is our constructions and the performance of the collaborative zkSNARKs that we construct. At a high level, our construction approach, I think, is very natural. Zero knowledge is in some sense our goal, and MPC seems like a powerful tool because we're imagining multiple provers. And in some sense, that's what we end up doing. But before I explain it to you, I have to talk about the scope of our construction. What kinds of properties do we allow proofs about, and do we make any assumptions about the format of the witness, how it might be distributed? The answer is that we do. So our focus is on building a proof system for a very particular family of relations, R1CS relations, and a very particular kind of distribution of secret information, namely secret shared R1CS witnesses. If you're not familiar with R1CS, that's okay. Just know that it's an arithmetic circuit format that's supported by traditional zero knowledge proofs. And so what we're imagining when we restrict our focus to secret shared R1CS witnesses is really a 2-stage process where only half of the process is the collaborative zkSNARK. Initially, you start off with your predicate, your property phi, and your secret information vector of W that is distributed. One entry is in the custody of each party. And you do not immediately write a proof about these things. What you do is you go through what we call a compilation phase. So you take the predicate, you feed it into a compiler, like, for example, Socrates is a compiler that people at Stanford use for this occasionally. And it spits out an R1CS predicate. So it translates the predicate from whatever high-level language you started with to R1CS in an equisatisfiable manner. But this compiler doesn't stop there. It also spits out an encoding procedure, really an encoding protocol. And the idea is that the different parties feed their witnesses into the encoding protocol together with the public data. And the encoding protocol spits out a witness now for R1CS. And it does a little bit more than that. It spits out that witness in a particular format. It secret shares it among the parties. So this encoder is some kind of multi-party computation protocol. And then what do? Well, you go ahead and write a collaborative zkSNARK now about your R1CS predicate and the secret shared R1CS witness. So the object that we construct really is this green box. And how do we do that? Well, like I said, there's a natural approach, which is to use multi-party computation. Generic MPC can evaluate any computation, provers included. And so by evaluating it on a zkSNARK prover, we should be able to apply that prover to a secret shared R1CS witness and get a proof about that witness. In theory, this checks all the boxes, and indeed, you can show that it satisfies the security definitions that we write down basically immediately. But there's a potential problem, and the potential problem is that this might be very slow. zkSNARKs are known for being very slow, and generic MPC is known for being around 1,000 times slower than the underlying computation. And so the fear is that when you take these two very expensive objects and you compose them, you might end up with a system that's 1,000,000 times slower than the base computation. It might take 1,000,000 times longer to write a collaborative zkSNARK than to just check the property directly, if the parties were to trust one another and share their information. And so the question really for us is whether or not it's possible to avoid this kind of millionfold slowdown, whether it's possible to avoid overheads that multiply. And indeed, we find that is possible. In some sense, the overheads, in a very strong sense, they don't multiply, they add. And the green box phase, writing the collaborative zkSNARK about the secret shared R1CS witness, we find that can be just as fast as writing a zkSNARK about a local witness, a local R1CS witness, or perhaps it can be 2x slower. And sort of the exact overhead here depends on the setting. like what the bandwidth is, how many parties there are, how complex the statement is. So to give you some sense of what that slowdown looks like, I'll share some of our experiments where we measure the performance of the systems that we implement. In this experiment, I'll be telling you about a collaborative zkSNARK, or really a collection of different collaborative zkSNARKs that we built, building on the Grot16 conventional zkSNARK over a very good network. So this is a 3 gigabit per second link. This is what you get inside of a data center. This is what you can get over a LAN. And so right now on the plot, I'm showing proving time for a single prover. So this is the baseline. This is not collaborative. This is just a local computation, and it's going to be a reference. We want to see how close to this we can do for collaborative zkSNARKs. The x-axis increases the number of rank 1 constraints, which makes the statement that you're proving more complex. The y-axis is proving time. And we see that the relationship is, it looks very close to linear. It's actually a little bit superlinear because Grot16's asymptotics are n log n, where n is the statement complexity. So what about a collaborative zkSNARK? How does it compare? Well, when we consider 2 provers with 0 knowledge against one of them being corrupted, what we see is that initially the overhead is a little bit larger, but once the number of constraints grows, the overhead, the increase in proving time, is only 2x. And when we consider 3 provers with security with 0 knowledge against 2 of them, we see the same behavior, essentially. The overhead is asymptotically 2x. While if we consider 3 provers with 0 knowledge against only one of them, so now we're assuming that the majority of parties are honest, the majority of parties are not trying to steal your secrets, we're able to use a slightly weaker but more efficient MPC, and we end up with overhead of only 1x. So this performance is somewhat encouraging because, as I said, many computations, when you try to securely evaluate them in an MPC, they slow down by a factor of like 1,000. And what we're seeing here is a slowdown of 1x or 2x. So this is a lot better. And of course, this performance does degrade in certain scenarios. So as the network capacity decreases, when we consider bandwidth on the order of megabit, the overhead grows. It goes to something like 10x when you get down to megabit speeds. And when you consider more parties, the overhead also grows. So I guess I'll stop talking about our work now, and I want to spend a few minutes speculating about what good directions for future research would be, or future development. One issue that our setup raises is this question of optimization and compilation. So this is the picture from before. In order to use a collaborative zkSNARK, first you have to compile your predicate to R1CS, and you have to run this encoding procedure that secret shares the witnesses. The interesting thing about this compiler here is that it's trying to produce an R1CS predicate and an MPC protocol. It's trying to do both these things. You want the predicate to be small, you want the protocol to be fast. And this implies that the compiler should be an optimizing compiler, but not just an optimizing compiler for R1CS or an optimizing compiler for MPC. It really should be an optimizing compiler for both at the same time. It's no good. It might be undesirable to make the R1CS predicate very small at the expense of blowing up the cost of encoding, or doing vice versa. And so we think that the design of such compilers is an interesting question. There's a compiler infrastructure, SURC, that we think might be well suited to this task because it can compile for both MPC and R1CS. But this particular question of how to jointly optimize, to our knowledge, has never been studied in any context. Another interesting direction for future work is what we call dynamic participation. So when you think about a collaborative zkSNARK, it has a lot of nice properties. It gives you public verifiability, it gives you privacy, but there's a downside. And the downside is that we assume that there is a fixed set of provers. The computation is a discrete entity that runs once. All the provers participate. We think that there are other contexts where it would be useful to have the set of parties change over time, and to imagine the computation is not something that runs once, but something that runs repeatedly on secret state. This is some notion of dynamic participation, where parties might join and leave the collection of entities participating in the MPC between each epoch. We're imagining really something like this. So you have some initial state and you run the function on it based on some input. The state right now is secret. And at the end, or in order to facilitate this, you have some collection of operators who run the MPC. But the output here is another state, which is once again secret. And so you continue. So it seems plausible that you might be able to have dynamic participation with this kind of public verifiability. Indeed, there's been some recent work into dynamic participation from MPC. And so it remains to be seen how it can be combined with notions of public verifiability. Okay, so I've been telling you about collaborative zkSNARKs. If you forgot everything else about the talk, remember two things. First of all, collaborative zkSNARKs support distributed secret information. Second, they can be shockingly efficient, at least when you can consider the performance relative to a conventional zkSNARK. And then finally, there's a lot of directions for future research. I mentioned the problem of compilation for zero knowledge and MPC. I mentioned the problem of dynamic participation. There are also other really natural directions. One of them is trying to build collaborative zkSNARKs that are post-quantum secure. We more or less strike out on this front, although we have some ideas about where to get started. And then, of course, one of the most interesting future directions is what you could imagine doing with tools of this kind. So maybe you want to build some kind of decentralized exchange that doesn't leak its state. Maybe you want to build some system that performs KYC without violating the privacy of participants. Maybe you want to encode some kind of group decision-making process where people's votes or in general the decision-making process is private. I think all of these are on the table. It's been a pleasure to tell you about this. If we want to take questions now, I'm happy to answer them, but maybe we're going to wait till the end. I guess I'll hand it over to Shashank right now, and he can make that decision.
Sorry, hi. Sorry, I wasn't able to unmute myself, but great talk, Alex. I actually have a lot of questions, and the performance numbers really want me to go and take a look at the paper and how to figure out how exactly you achieved them. But yeah, we may not have time for questions now. We could try to see if we have time at the end, and we also have a couple of questions from the audience. So let's see how much time we have left at the end to answer those. Yeah, thank you. The next talk is going to be by Pratyush Mishra, who is an assistant professor at UPenn, and he'll talk about efficient private delegation of zkSNARK provers. Pratyush.
Hi, everyone. Let me just share my screen. Give me a second. Let it up again. All right. So let's play the slideshow. Okay, I think you should be able to see my screen. Okay, yeah, I think nobody said no, so I'll continue. Okay, so hi everyone, fantastic to be here. Yeah, so in this talk, I'll talk about, I guess, one specific application of taking MPC techniques and applying them to zero knowledge protocols. And this sort of is very similar to the techniques in Alex's work that he just talked about. All right, so this is a paper about outsourcing zkSNARK provers from a computationally weak device to a potentially more powerful device to sort of reduce the overhead of participating in zkSNARK-based applications. Okay, all right, so I'll quickly cover what zkSNARKs are because we've already had a sort of whirlwind overview of those. But basically, they're a protocol between a prover and a verifier. The prover wants to convince the verifier that it knows some private input or private witness, which satisfies some functions. So you can think of, for example, it wants to claim that it knows the pre-image to some public hash, right? What a zkSNARK allows the prover to do is produce in a basically quasi-linear amount of time a very short proof that the verifier can then check for correctness in a logarithmic amount of time. And the two properties that we're interested in from zkSNARKs are first zero knowledge, which basically means that the verifier learns nothing about the prover's private input, except for the fact that it satisfies the function, and succinctness, which means that the proof is short and can be checked in time much less than running the function itself. Okay. So there's a tons of applications of ZK, just even in the blockchain space, for example, there's things like private transactions, private smart contracts, decentralized multiplayer games. And then outside that scope, there's things like anonymous credentials, proving existence of vulnerabilities, voting, and so on. Okay. So this is fantastic, but there is a bottleneck to actually deploying these applications, and that is that proving is really slow, right? For example, just proving that you hashed 10 kilobytes of data with SHA-2 takes an inordinately large amount of time, like over 2 minutes, with relatively state-of-the-art proof systems, but natively it just takes a few milliseconds at most, right? Probably more on the order of microseconds. Okay, so one solution that people have come up with in the past is to try and outsource the proof generation, right? So this computationally weak device, for example, a mobile phone, will send its private witness to some more powerful server, and the server will do the work of generating the proof and will send the proof back to the device, to the client device, who can then, use the proof in the application. Okay. So there's been one work at Usenix 18, so a few years ago, which shows how to do this for a cluster of machines, for a Spark cluster, and they're able to get fairly good scaling. In fact, I think they get sort of linear scaling with the number of machines that they have. So yeah, in practice, you can do this, for example, at least for the Groth16 protocol, right? But there's one downside of this, and that is this cluster of machines, or this outsourced, more powerful machine, it learns the secrets of the client, right? So the client has to send this private witness over to this set of worker machines. Okay. All right. So how can we get rid of this limitation, right? So what we want to do is we want to be able to outsource proving with privacy. So we want to have some delegation protocol that the prover and the workers interact via, in such a way that it hides entirely what the witness is, right? So there's no leakage about the witness of the client. Okay. And so they interact in this delegation protocol, and at the end, the prover, the client device gets its zkSNARK proof as it wanted. Okay. And there's a couple of goals that we want from this from such a scheme. First is efficiency, right? The delegator's work in participating in this delegation protocol should be much less than just generating the proof itself. Otherwise, the delegation protocol is kind of useless. Okay. The second goal is privacy, right? The delegator's witness should be hidden from the worker. Otherwise, we could just use the DZIG technique from the previous slide. All right. But the problem is that, as far as we know, at least, it doesn't seem possible to achieve this without using heavyweight tools like fully homomorphic encryption, right? You could use, for example, fully homomorphic encryption to just encrypt the witness with the FHE, and then the worker will evaluate homomorphically the zkSNARK proving algorithm over the private witness. But this is going to be really, really slow. So, Alex mentioned if you just use generic MPC, you get like a 2 million X overhead. Probably it'd be much higher if you used FHE for this task. Okay. So what we'll do is we will relax our goal. Instead of going for privacy against instead of having just one powerful worker, we will instead say, okay, we have a few different powerful workers, right? And as long as some subset of those is honest and is not colluding with the other workers, we'll get privacy, right? So, right, basically the goal is that the workers sort of interact among themselves to compute the proof and send it back to the client device. And the privacy goal has now changed in that the delegator's witness should be hidden as long as at least one worker is honest. So you could have like n-1 workers be corrupt, but at least one of these is honest, then the privacy of the client's witness is preserved. Okay. So how can we achieve this more relaxed notion of privacy, right? And this is the topic of this work, right? So what we do is we show how to delegate zkSNARK proving for proof systems based on polynomial IOP. So this includes things such as Plonk, Marlin, Halo, Sonic, basically every recent proof system that people have been interested in. So in particular, we show how to construct delegation schemes. I guess to do this task of constructing delegation schemes for polynomial IOP-based SNARKs, what we do is we first construct delegation schemes for the two components. And these components are polynomial commitments. So we show how to construct delegation schemes for KZG and inner product argument PC schemes, and for polynomial IOPs. In particular, we focus on the Marlin IOP. And then we show how to combine sort of these components generically. So a delegation scheme for the PC scheme and a delegation scheme for the polynomial IOP. And we show how to generically combine these two schemes and get a zkSNARK get a delegation scheme for the whole zkSNARK. Okay. And so this is not just a theoretical work. We implemented and evaluated our protocols, and we found that delegating, for example, from a mobile phone is up to 26 times faster than just computing locally. Okay. I'm not sure how much time I have, so I'll sort of try to speed up the rest of the talk. All right, so let's see how we can actually construct the delegation scheme. And a starting point would be to use MPC. So just like Alex said, right, you could try to use a generic MPC protocol, and just recall that MPC sort of enables a bunch of people to come together and perform a joint computation over secret data, right? In this case, the secret data is the client witness. Okay, so we can just throw MPC at this problem, but there's two issues, right? First of all, just taking a generic off-the-shelf MPC protocol would require expressing the prover's algorithm as a circuit over some finite field, right? And the problem here is that this resulting prover circuit becomes very large for popular zkSNARKs. So this is basically where the 2000x overhead that Alex mentioned would come into play, right? So why is the circuit large? Why is there this like 2 millionx overhead, I guess, overall? Is because focusing on, I guess, these polynomial IOP-based SNARKs, they consist of two things. They consist of the prover circuit for the polynomial IOP. So you can think of, the techniques in Malin, Planck, P-lookup, Lunar, Halo, etc. And they consist of circuits for the polynomial commitment scheme, right? This is committing and proving evaluations. All right, and the reason why these circuits are large is first they are sort of happen over different fields. So actually, if you just try to combine these subcircuits together naively, you'll end up with a very large circuit. And individually, even sort of these subcircuits can be quite large, right? So even before you try to join them, the individual subcircuits can be quite large. So let's see how we can tackle both of these problems. Okay, so I won't recap about how you can construct a SNARK from a polynomial IOP plus a PC scheme. But basically, the idea is that in the protocol, the prover sends some commitments to polynomials, and at the end, the verifier queries these commitments, and the prover provides an evaluation proof that the commitments evaluated at those queries sort of lead to the expected evaluations. Okay. The building block for our techniques will be additive secret shares, right? So an additive secret share basically just says that I can split up a message into some set of secret shares, such that if I add up these secret shares, I will recover the original message. But if I have, even n-1 out of n shares, I will learn no information about the message. Okay. All right. The nice property of these additive secret shares that we will leverage is that they have an additive homomorphism. You can add two shares and you will get a share of the result of the addition of the underlying messages. Okay. All right. So let's see how we can tackle each of these subproblems. So to tackle the problem of sort of combining these subcircuits, what we'll do is we will take advantage of the modular structure of these zkSNARKs. So instead of trying to construct one mega MPC for the entire zkSNARK, we will instead first construct an MPC for delegating the polynomial IOP, and then we will construct an MPC for delegating the PC scheme, and combine these to overall get an MPC for delegating the zkSNARKs, right? So basically what this will look like is that the client will send secret shares of the witness to the workers. They will engage in the PIOP MPC. They will get secret shares of some polynomials. Then they will invoke the PC scheme delegation and get out secret shares of the commitments. And they will repeat this over and over until they have like a vector of each of these, right? And finally, they will invoke the PC scheme MPC for generating an opening proof. Okay. And they will send these secret shares of all of these things back to the client, who will combine these and obtain the actual zkSNARK proof. Okay. So that's basically how we will tackle these two components. And let's see how we can actually basically now, instead of doing one mega MPC for both of these, now we've separated each of these. We've taken the output of the MPC, for example, of the PIOP, and fed that into a separate MPC for the PC scheme. And we repeat this process iteratively. And this is basically how we avoid combining these expensive these subcircuits in an expensive manner. Okay. So let's see how we can actually now reduce the cost of each of these subcircuits. And yeah, where we'll focus first on PIOP delegation, and then we'll focus on the PC scheme delegation. Okay. So the flow basically looks like you have some state for the polynomial IOP prover, and you want to do an MPC for delegating for doing the next round function of the polynomial IOP and getting sort of the next round message, which is the polynomials. Okay. So if you look under the hood of what these polynomial IOP provers do, they basically do a bunch of arithmetic with polynomials over finite fields. This includes things like evaluating polynomials over subgroups, evaluating polynomials by the vanishing polynomial for that subgroup, some linear polynomial operations, and finally some polynomial multiplications. Now, the good thing for us is that most of these operations can be performed just using addition gates, right? So we can directly leverage the homomorphic property of these additive secret shares and compute these three operations very efficiently. But polynomial multiplications, they involve a multiplication, so we can't just use addition gates. So recall that to multiply two polynomials, just even in a standard algorithm, first you need to, the standard way to do this is to use the FFT to get their evaluations over some large domain. Then you multiply these evaluations in a pointwise manner, and then you invoke the inverse FFT to sort of recover the coefficients of the polynomial product, right? Now, steps 1 and 3, they're again linear because the FFT is a linear operator, right? And so is the inverse FFT. So the only thing we need to worry about is step 2, how to do this pointwise multiplication. Thankfully for us, there are lots of standard techniques in the MPC literature for doing pointwise multiplication, but we actually don't need that in our setting because in some sense, there is a trusted third party who can perform the polynomial multiplication or the pointwise multiplication for us. In particular, what we can do is we can have the workers send their secret shares of the inputs to the multiplication gate back to the client, and the client will then perform the multiplication and send back the shares of the result to the workers who can then continue the rest of the computation. Okay, and basically by doing this, we don't need to invoke any cryptographic machinery or have pre-processing, though we have support for that also in our system. But yeah, this is one way to implement the multiplication gate. All right, okay. So this means that for our polynomial IOP, we can either do most of the work without any interaction, i.e. we are using the homomorphic addition, or with just one interaction with the delegator. All right. So that covers the PIOP schemes. Together, this sort of gives like a low depth, low multiplication count. So I guess just to summarize, we're now, with these techniques, we're able to get a low depth and low multiplication count circuit for most polynomial IOP provers. Okay, for the PC scheme, I'll focus on the KZG scheme because that's what we evaluate. But basically, again, if you look inside the algorithm, what you'll find is that it's, again, mostly a linear operation, right? So given a secret share of the polynomial, I can get a secret share of the commitment to that polynomial because the commitment is basically a Pedersen commitment, which you can, which is a sort of linear operation over the group elements. Similarly, the computing and evaluation proof can also be done in a linear manner. So again, delegating the PC scheme requires no interaction between the workers. It's an entirely homomorphic operation. Okay, and in particular, the complexity will be the same as standard KZG. There's no interaction required. Okay, so the same, yes, very similar techniques were also in Alex's work and another prior work for delegating. I think they were focused on the IPA PC scheme. Okay, so there's tons more optimizations that you can cover that you can do both at the systems level as well as the crypto level. I won't go into them here. I will just quickly jump to the final concrete performance improvements. What we found was that after implementing, so we implemented in the ArcWorks library all of these components. What we found was that on a laptop with a good internet connection, like let's say gigabit speeds, we were able to get a over 10x reduction in proof generation and almost 600x reduction in the active computation time for the laptop, right? So the laptop was only doing computation for, I guess, 1/600 times the computation that I was doing if it was making the proof itself, okay? Furthermore, by outsourcing to more powerful machines, we were able to sort of, like actually most zkSNARKs, they're not bottlenecked on proving time, but often they're bottlenecked on the sort of memory, because the FFT is a memory intensive operation. So by outsourcing to more powerful provers, we were able to increase the provable instance size by over 256 times, right? If you have a less powerful internet connection, obviously these numbers degrade because the time to send the witness starts to play a larger factor in the overall delegation protocol. But we're still able to see some reductions, and we still have this reduction, this improvement in the provable instance size. Finally, we also benchmarked delegation from a phone, and what we found was that obviously this is the best case because the phone is the weakest device. We found the latency of end-to-end proof generation was reduced by 26 times. And again, we were able to prove 256x larger instances. Okay, so sort of, yeah, the summary of this basically is that the delegation schemes are actually able to provide a benefit in terms of outsourcing, even if you're using these complex-ish MPC techniques. Okay, so yeah, thanks everyone for listening. Paper is coming soon to an ePrint, and the code is also, we'll put it online soon. At the ePrint, I think we'll try to put it online within the week.
Cool, Pratyush. Very nice paper and very nice talk. Well, the paper is not out yet, but I'm sure it will be great. Do we have any questions for Pratyush?
Oh,
yeah,
something in the chat.
Yeah, I don't see anything right now. There has been some discussion here, but it seems to be mostly about Alex's paper. Anyway, we probably don't have time to take questions at this moment. But yes, great talk. We'll come back to this at the end of the session. Let's move on to the next speaker, Elette. She's an associate professor of computer science at IDC Herzliya, and she'll talk about zero-knowledge proofs on distributed data.
Hi, everyone. Let me share my slides here. So welcome everyone. Hope those who are submitting to the Eurocrypt deadline that is impending are taking a little bit of break from that. So as Pratyush and Alex talked about some topics that are also going to be coming up a little bit in my talk as well. So I'll be speaking about zero-knowledge proofs on distributed data. That probably sounds very familiar given the first talk here. And I'll specify a little bit about how they're different. In any case, this sort of predates, it's old school now in comparison. So this is based on a line of work together with predominantly Dan Bonnet, Henry Corrigan-Gibbs, Niv Gilboa, Yuval Ishai, and Ariel Noth. And I'm going to be keeping things relatively at a high level, but feel free afterward to ask questions. And just one clarification before I move on. So I have a lot of different affiliations here. IDC Herzliya actually recently changed its name to Reichman University, which is why that's there. And I'm also somewhat recently a senior scientist at NTT Research. Okay, so I can probably skip this slide for this audience, but just a quick recap. In standard zero knowledge, we think about a setting with a single prover and verifier. Okay, where both prover and verifier are aware of some input X and some language L, and the goal of the prover is indeed to prove in zero knowledge to the verifier that X is a member of this language. Okay, so I'll be talking about zero knowledge on distributed data in a similar way as in the first talk, where this input X is actually not known by any individual verifier. Okay, so one little bit of a distinction, we do consider that the prover knows the entire input X, but that X itself might be split in one of a couple different ways across a collection of verifiers. So this can be secret sharing, perhaps an additive secret sharing of the information, perhaps distributed in the sense that the first verifier has the first sequence of bits versus the second sequence and so forth. And kind of more generally, the property that we need is that there exists some public linear combination of what the verifiers are holding on to that reconstructs this input X. Okay, so the properties that we'll want are somewhat similar as usual. So completeness in the sense that if this X truly is in the language, then an honest prover should be accepted. Zero knowledge here, note that there's a little bit of a subtlety, where if you have a subset of corrupt verifiers, they should learn nothing, of course, beyond the fact that whatever this X is that recombines is in the language. But note that in particular, they should not learn anything else about X itself. Okay, so nothing beyond what they held beforehand, which is really just this combination of pieces Xi of corresponding to the corrupt shares. And in regard to soundness, so let me first consider a case. Suppose it's you're in a setting where the prover is corrupt, but cannot collude with any of the verifiers. Okay, then sort of soundness is straightforward, that if an honest verifier accepts, that should mean that indeed X is in the language. And it turns out that actually even defining the soundness in the setting where prover can collude with a subset of verifiers is a little bit more subtle. For example, what does it even mean? What is X, right? What are we proving is in the language? I'm not going to get deeper into that for the purposes of this talk. You can ask me about it later. But roughly speaking, what you need for this to make sense is that there's some sort of robustness of X, of this split or sharing across the verifiers, in the sense that whatever the pieces are that the honest verifiers are holding on to actually does define some statement X. Okay, so this is sort of the object of the talk today. Let me make a couple brief remarks first of all. So in contrast to standard zero knowledge, the fact that no individual verifier actually knows X means that such a proof system is non-trivial even for very simple languages. Okay, so for example, if my language L was easy to verify, then in the standard setting, I can give you a zero knowledge proof of X being in the language by just sending you an empty string, okay? And you as the verifier, you can just check on your own, is X truly in the language or not? You're not learning anything beyond the statement. Okay, but in this case, because nobody actually knows what X is, possibly, this is already interesting even for simple languages. And in fact, I'm going to be focusing on quite simple things. For example, that I want to check that different symbols of X satisfy some even degree 2 or low degree relation with each other. Okay, and another remark here is that because of some of these changes in different application settings, there's some different complexity goals or different types of metrics that come into play than you would typically think about. And one of those is the proof size, or rather here, so in this model, we're thinking about the prover sends some information to each of the verifiers. Okay, and this could potentially be a little bit of back and forth. And the verifiers as well will do a little bit of communication. But as we'll see later on in this, definitely in one of the applications, the amount of communication here, we'd like to keep that quite low. Okay, so in my limited time, I'm going to sort of zoom through a couple of things, but I want to give you a bit of a flavor of how do we build such a protocol, or really what do we know that's interesting that exists for these things. Okay, so I could give you a whole nother talk about this other notion. So the way that we build these, here I'm denoting this by DZK for zero knowledge on distributed data protocols, are via a tool that's related to standard probabilistically checkable proofs. So again, probably luckily this audience is likely aware of these things, but a bit of a twist on the standard PCP that we refer to as being a fully linear. Okay, so those who have seen linear PCPs, this is a version where the verifier knows the input and can make linear queries to the proof. Whereas a standard PCP, you know the input and you can make individual probing queries to the proof. And this fully linear PCP is a new object that we put forth in a paper from a couple of years ago, which sort of extends these, where the verifier does not have access to the input, but instead can make linear queries that go across and combine between the input and the proof. Okay, and it turns out, so basically this is some sort of information theoretic object, and if you can build a fully linear PCP, or here the interactive version, an interactive oracle proof, which has this fully linear property, then there's actually, I would leave this as an exercise to this audience of how can you convert such a thing into a zero knowledge. So if you also have zero knowledge, I suppose, on the fully linear PCP, that how you can use that in order to get a zero knowledge proof on distributed data. Okay, so that's all I'm going to say about that for now. So what exists? What do we have? And it turns out that a lot of different tools are for building such a thing are actually existing already in the literature. So if you go back and look at quite a few different results, for our setting, we in particular the fact that we want zero knowledge and we want these very short proofs for simple statements, we do provide constructions directly, building on the ideas of some check protocols. And maybe just sort of summarizing, so this is the Crypto 2019 paper. So for again, these very simple sorts of languages, here I'm describing the language L. So these are, length n strings of field elements, okay? And the language is defined by, first of all, if you have some sort of degree 2 relation, okay? So for example, say that the first symbol times the second symbol of X is equal to the third symbol, or some sort of generic circuit expression of degree 2 across many different symbols of X. So such a tool can exist. So this zero knowledge proofs on distributed data with a proof size, and this I want to emphasize, the proof size is sublinear in the input size. Okay, so again here, the length of X is n symbols, and we're talking about communication of roughly square root n symbols of this field. Okay, and extending this, if you allow interaction, here are logarithmically many rounds of interaction between the prover and the verifiers, you can crank this down all the way to logarithmic in the statement size. And this is even slightly more general, where you can handle general constant degree relations over F. Couple remarks about this. First of all, you won't see, I didn't write any computational assumptions in this theorem. This is because there are none. So these are purely information theoretic tools. There's no polynomial time adversarial assumptions or anything of this form. And further that, so here this error, this is the soundness error, scales as 1 over the field size. So this is kind of with regard to whatever field your symbols are in. Okay, if my field is F2, if these are bit strings, this looks a little bit pathetic, but don't worry, because there's a simple way of extending this for if I want even a small field, that you can really amplify the error down via kind of standard tricks of a ring or field extensions. And one thing that I want to mention here is that this still keeps the size of the proof, the communication overall is sublinear. So yeah, with some sort of cost relating to the field size, but as you'll see in applications, it won't bring in other terms. Okay, and one final kind of remark here. So this gives you, the second line gives you much better parameters, logarithmic versus square root, and also larger degree, at the expense of interaction between the prover and the verifier. And the comment here is that in a sort of standard type of way that you can collapse this down to make this non-interactive via techniques with Fiat-Shamir. Okay, so this is a little bit about what is the object and what do we know about it. And I wanted to close with 2 kind of broad classes of simple applications. And this by no means is an extensive list of things. These are really just a couple different flavors that come up. And I really actually, I invite you guys to come up with even more applications. Okay, the first category of application I'm going to sort of roughly define as private aggregate statistics. Okay, and let's think about a concrete example. Suppose that I'm a company and I want to maintain some sort of website traffic data, okay, or maybe even broader than a single company. Okay, so for each client, somebody who's accessing some item, if we have a single database that's holding on to these things and incrementing, this is sort of the simplest naive approach. But as you know, this is becoming a bit of a problem in many different ways, in particular that this is sort of violating the privacy of individual clients. So this is getting to be a really touchy subject, and a lot of companies are turning towards solutions where they don't hold on to this data, even if the clients don't mind. There's a lot of a burden of holding on to such information. Okay, so instead of holding this at a single place or having some single location that knows the information, one promising approach for doing this with sort of low cost is that you instead split this across 2 or possibly more servers. Okay, so for example, there's different services that are starting to sprout out of playing the role as the second server. So one server can be, for example, held by the company, and one would be external in one of these other individual services. Okay, so what happens now is that instead of any individual location actually having access or having information about the real counts or the real information as individual clients come by, that the servers will split this information and store instead a secret shared version of these histogram counts. Okay, so now as each client comes and actually accesses a website, instead of just sending a direct, this is my website, they'll instead have some sort of split information. And again, I will direct you to, if you guys have heard of function secret sharing or perhaps distributed point functions, this is one explicit way that you can implement this, that effectively, this is a compressed secret sharing of a giant unit vector that the servers would be able to expand out and then be able to increment their individual secret shared databases. Okay, but let's even keep this more abstract. So say that there's some way of splitting this information of what was the website, the URL that was actually being accessed, split into 2 parts and give one share to each of the different servers. Okay, and now somehow, assuming everybody did this correctly, then there's some cheap way of taking this and kind of expanding this out, as I mentioned, to modify each of these counts. Okay, so pause here. I haven't said anything about proofs at all. And that's because up till now, I'm assuming that each of these shares are totally accurate, that they're well-formed. Okay, but suppose it's not the case. Even using this approach, even if a single client is malicious and gives some sort of malformed shares, this could completely destroy the entire histogram up to this point. Okay, so for example, if somehow these values, these red values here, if instead of actually expanding to secret shares of a unit vector, like they're supposed to increment, if they were just shares of totally random garbage, then this, by incorporating these shares into the this histogram that's running along, this would completely destroy all the information up till now. Okay, so because of that, we want some sort of efficient way that before the servers will actually incorporate a client's information, that they would have some way that they can check that these shares were actually correctly formed. Okay, and if you pause for a second and kind of take a look at it, this can exactly be cast as a version where the client is serving as a prover. Okay, and the verifiers are these 2 different servers. And the client needs to prove to the servers that whatever pieces it sent are actually consistent with the language it's supposed to be in. Okay, good. So this is one category. The second category, so this is a zkMPC event. So certainly it's appropriate to talk about secure multi-party computation, or MPC. And indeed, this is a category where these tools have really actually shown a lot of useful different applications. Okay, for those who, perhaps if there's somebody in the audience who's less familiar, let me just briefly mention. So here, when we're talking about multi-party computation, this is some way that a collection of parties that each have some secret input information, here denoted xi, okay, will be communicating with each other with the goal of jointly computing on the secret data without revealing this data. Okay, so concretely, if there's some public function f that everybody knows, and the goal is by speaking back and forth, that we learn f evaluated across everybody's global inputs, but without revealing anything else about the inputs themselves. Okay, the interesting part for today is that this should hold even if a subset of parties are adversarial. And what exactly do we mean by adversarial? Well, within the MPC literature, there's a few different types of adversarial models. But ultimately, the goal is sort of standard or full or active security, where even if some of these entities here are sending bad messages or they're trying to ruin the protocol, that you still will guarantee that you have privacy and correctness. Okay, so this high level is the goal. But if you go back in essentially all constructions of MPC protocols that actually achieve this high level of security, take the route of first building a protocol with a weaker passive type security, okay? Where here it's assumed that actually everybody is following the protocol, okay? So if it has some sequence of steps, you're supposed to sample random values, send some message, so forth, that the parties will actually perform those steps as dictated, okay? But the adversarial sense is that perhaps they're combining information in ways that they're not supposed to. Okay, so it turns out it's much easier or more direct to be able to build these weaker sorts of protocols. And then what happens is that there's some kind of compiler that pushes you from passive security up to active security. Okay, and this dates back to the original secure computation protocols in the 80s. So for example, in the original compilers, what happened is that you would force passive behavior by zero knowledge. That roughly for every single message that you're sending, you would accompany this with some sort of zero knowledge proof that this was indeed the message you're supposed to be sending. Okay, so fast forward a couple of decades, and now there are quite a few different ways of enacting this compiler from passive to active security. Maybe you could take a look, maybe you've seen some of these things before. And the punchline that I want to give you is that using zero knowledge on distributed data gives you a new way of building such a compiler with very beneficial properties. Okay, and in particular, so before this line of work, if you looked at each and every one of these approaches on this list that was in some sort of, okay, so I'm pushing fully homomorphic encryption to the side. But for example, for any protocols without FHE, that in order to do these compilers, and this is the regime of a lot of work of efficient MPC, that the overhead was some sort of at least constant multiple of communication complexity. Okay, and so now using these tools, this gives you a way, for the first time at the time, now there's been a lot of development since, that you could achieve this active security where the additional communication complexity that you need is sublinear in the total communication. Okay, I'm almost.
Yeah, I'm sorry, I would have to stop you because we may not have enough time left for the last speaker. But great talk, very informative, and thank you also for talking at great length about the applications of your work. Yeah, I'm sorry, but
It's no problem.
Stop you there.
Yeah, so I'll leave this up as a mini summary.
Right, and the paper is also available online, right? So where could we?
Yes, there's a collection of papers, and they should all be online.
I see. Okay, yeah, cool. Thank you so much. So we have about 20-25 minutes left in this session. Let's go to the last speaker, Ran Hindi, who is CEO at Zama. He'll talk about private smart contracts using homomorphic encryption.
Great. Hey, everyone. So I guess I'm going to do a talk that's a little bit less, well, a lot less technical than the ones before. Apologies for that. But if you like to get into the hardcore details of homomorphic encryption, there is actually a community called fhe.org where we have monthly meetups where people present the latest research results. So this is more going to be a protocol level, not math crypto level. Let me share my screen. I'll try to make this quick, by the way. I realize it's a little bit short on time. Great. So what I'd like to talk about is how you can use homomorphic encryption to enable private smart contracts. So the problem with blockchains today, of course, is that everything is public. And why is everything public? Well, because you need to agree on what has been done. And so far, the only way to do that was to share everything publicly. The problem, of course, test surveillance, importantly, MEV, so those front-running bots, which are annoying to everybody right now. All of these things can basically be solved using homomorphic encryption. So the idea of FHE is that you can basically apply a function on a ciphertext, and what you end up with is an encryption of the function applied on the data that's inside the ciphertext. So more generally, F applied on encryption of X equals an encryption of F of X. So this is not a new idea. This is something people have been thinking about for a very, very long time, but it has only started to be practical recently. So if you want to understand where FHE is in terms of maturity, it's basically where ZK was 3-4 years ago. So why is that useful for blockchain? Well, because it means that you can actually encrypt the transaction data. So when a user is making a transaction with a smart contract, instead of actually revealing all the content of the transactions, they can actually have ciphertext included in transactions. The validators who then execute the smart contract will basically run encrypted computation on those encrypted inputs. And finally, the data that's stored on chain will also be encrypted. So this is great because it means it's impossible for people to know how rich you are, how many tokens you have. It's impossible for people to see the data you have on chain. And importantly, it's impossible for bots to actually front run your trades because they actually have no idea what you're currently doing. It also opens up a bunch of new applications. So for example, everything related to on-chain identity. There's no way people will store their identities on chain and compute on them if everything is public, of course. But also, NFT metadata, which can become secret, and more generally, usage of any kind of personal data in a smart contract. So how does that relate to ZK? So ZK is used, of course, for scalability, but it's also used sometimes for privacy. And the way I like to think about it is that, zero knowledge really hides the metadata. It's a way to remove the trace of the transactions on chain. But if you want privacy with regards to the data, you typically are doing it off chain at the moment. So homomorphic encryption is complementary to that in the sense that the actual traceability, the transaction is completely public, but the data it contains is private. So FHE is private data with public metadata. ZK is public data with private metadata. And of course, if you can combine both, you can have private data with private metadata, which would be really amazing. So one parallel to that, by the way, is, ZK privacy is a bit like Tor, right? So, the content is public, but the route to get there is private. FHE is more like Signal. The actual content is private, but the operator can see who's been talking to whom. So let's give you a very brief introduction to homomorphic encryption and the reason why this is very difficult to use in blockchains right now and how we're solving that. So at a high level, a ciphertext in homomorphic encryption is basically a message plus some random noise encoded into 32 or 64-bit integers. So each of those squares here, you can think of it as a bit on the physical integers in your machine. So typically you put the noise on the right and then you put the data on the left. And this is fine if all you wanted to do was decrypt, right? Because you just cut off the noise and you still have the data on the left. But if you want to do some computation, let's say, for example, additions or multiplications, not only are you doing that on the bits of message, you're also doing that on the bits of noise. And eventually the noise will start running out of space to grow and will start overflowing on the significant bits of data. So if you're lucky, you're going to get an approximate result. If you went too far, you're going to get a completely incorrect result. And effectively, you're going to have a random value out of it. So this is what we call leveled homomorphic encryption. You can basically do homomorphic computation up to a certain number before this noise component grows too big. So in the case of a blockchain, this is a real problem because, well, you're not decrypting the states. So for example, an ERC20 smart contract, if I'm sending some tokens to someone, the actual balance, which is stored on chain, if you wanted this to be a ciphertext, you're potentially making an infinite number of operations on this ciphertext without actually decrypting it. And so eventually, you're going to run out of budget to actually do those computations, and the result of the balance transfer will be wrong. So this would be really bad. It would basically make this whole thing completely useless, which is why we need to use another technique on top of those operations, which is called bootstrapping. So the idea of bootstrapping is that once the noise grows too much and is basically on the verge of overflowing on the actual data, you stop what you're doing and you basically do this special cleanup operation, which resets the noise to a nominal level. So you can think of it as homomorphically doing a decryption and re-encryption, right? So you're basically removing the data and just putting it back as if you just had a fresh encryption. So this is great because it means that you can keep on going forever. You don't have to worry about noise accumulation, but it's also very slow. So when people say homomorphic encryption is slow, it's not because of the actual homomorphic computations. It's actually because of the bootstrapping operation, which is necessary. There's another problem, though, with existing schemes, which only enable additions and multiplications, which are that it doesn't give you a way to do exact nonlinear evaluation. So, for example, if you have an assertion in your smart contract, you want to check if the user has enough balance, or maybe you want to compute some nonlinear mathematical function, you would need to approximate it with a polynomial approximation, which could be okay, but it would be extremely ineffective in terms of eating up, your noise budget. So that's a real problem, right? So you need to be able to do those exact comparison, those exact nonlinear functions without having to worry about approximations. So for this, you can use a scheme which is called TFHE. So TFHE enables very fast bootstrapping, but importantly, the bootstrapping itself is actually programmable. So the bootstrapping operation, what it does in practice, is a homomorphic lookup table. So you can encode any function as a lookup table, and as you're bootstrapping, you can basically evaluate that function on the ciphertext. So if you just want to remove the noise and you don't want to compute a function, you're just using the identity function, but you can now use that to do comparisons. You can now encode, a logarithmic function and whatever crazy stuff you might want to do. And so instead of having circuits of additions and multiplications, what you end up with are functional circuits, basically linear combinations of univariate functions, which we're evaluating through this lookup table approach. And this is a very, very powerful paradigm for representing circuits. It's actually what a neural network is, by the way, if you were ever wondering. And there is even like a very nice theorem from Kolmogorov that basically says that any multivariate function can be represented as a linear combination of univariate functions. So this is the idea that you have behind TFHE. So with TFHE, you can basically evaluate any kind of operation exactly on a smart contract without having to worry at all about approximations or incorrect result or noise accumulation. So in terms of performance, what we're seeing right now is that there is a 10x performance improvement on homomorphic encryption every couple of years or so, mostly driven by hardware acceleration. So what we estimate is that by 2025, you will have the first FHE ASICs available on the market, and that will make FHE fast enough for 80% of cloud or blockchain use cases. So it's a technology that you can consider mathematically solved, and we just need this extra acceleration to basically make it applicable to pretty much everything. So let's talk about how to use that specifically in a smart contract. The goal here is that a developer shouldn't have to worry about cryptography, right? There shouldn't be any parameters to optimize. There shouldn't be any kind of concept of keys or anything like that, because that's always very complicated. So the way this works is that you've got a high-level front end, so typically Rust or Python in the case of what we do at Zama, which enables you to express your program as a traditional program, just with this addition of encrypted variables. So, your integer in your balance map is now just replaced by an FHE integer, but everything looks exactly the same. There's one tiny, big difference actually, is that you don't want everybody to be able to see the actual values of other users. So you need to basically have a way where you can re-encrypt the data from the encrypted on-chain state to a specific user's key so that only a specific user can see it. So we can call that like a key switching or re-encryption operation. But there are three problems in trying to do that. The first one is, because you've got multiple parties interacting with the same smart contract, who holds the key that people are using to interact together, right? Because you need to have all of those ciphertexts encrypted under the same key to be able to be compatible. So how do you prevent someone from accessing the network's key and decrypting everything? The second problem is, well, how do you prevent the validators who now have to be able to do things like verifying, that you have enough balance to request incorrect decryption from that private key? So how do you guarantee that the validators are making honest decryption requests? And finally, how do you prevent users from just taking some public material on the blockchain and somehow pushing like a smart contract to decrypt it and see the values of other users? So these are like fundamental problems that you need to solve. So the security is the, well, easy in theory, very hard in practice part. Basically, you do a threshold homomorphic encryption protocol. So the validators act as a multi-party, as an MPC protocol for threshold decryption and threshold key switching. So this is something that's quite difficult to do with FHE, but it exists. And so the constructs are being implemented and tested at the moment. So I don't need to explain to people here what threshold MPC protocols are. I think everybody's already very familiar with that. The only caveat, however, is that you cannot have an unlimited number of validators because that would be prohibitively expensive. But this should work with most flavor of, delegated proof of stake, nominated proof of stake, or for that matter, pretty much any chain that doesn't have 4,000 validators. What's more complicated is dealing with the requires. If you remember, when you look at your smart contracts, you've got this require. You need to check that the user has enough tokens or whatever to be able to execute the transaction. Because if this condition fails, you're supposed to revert the transaction. But how do you actually verify a condition on encrypted values where you're supposed to be invalidating a transaction in the block at the end? Well, for that, what we are proposing here is to basically bake the actual threshold protocol into the consensus protocol so that when the validators are actually engaging in consensus, they're each doing the same computation, applying their part of the threshold decryption. And then if there is a 2/3 consensus or something like that, then you can basically see that, oh, this transaction is wrong, and you can remove it from the block before you finalize it. So you can do that as a separate oracle, or you can do it as part of the consensus protocol. It's kind of up to you. Then finally, the last problem is, how do you make sure that the inputs users are sending in the transactions, the ciphertext included in transactions, are actually generated by the user and are not public key material? Because we've got basically a decryption oracle, and that means that anybody could send a malicious smart contract and decrypt anything. So for that, you need a zero-knowledge proof of input awareness. So effectively, when the user is encrypting data to be included in a transaction with a smart contract, he or she needs to provide a zero-knowledge proof that they know the actual inputs of the transactions. And so by doing that, the validators can verify those proofs and be like, okay, so the user does know the value, therefore he's not trying to cheat and decrypt someone else's material. I can actually accept that. So overall, the protocol, basically you're encrypting inputs, generating the proof of plaintext awareness, sending that to the network, checking proofs, executing the FHE transaction, doing the threshold protocol, doing the key switching so users can see what they own, sending back the response and decrypting the results. So it's a pretty complex protocol because it involves mixing FHE, MPC, and ZK, basically. But importantly, it works. And we should have something in testnet in the next 6 months. So we're pretty excited about that. It'll be very slow, don't get your hopes up, but it'll work. And that's the important thing. So future improvements. So we are working on provable FHE. So it's very easy to prove the leveled additions and things like that, but it's very difficult to prove the bootstrapping operation because it's a huge operation. It's basically, it's a huge operation. But this would be very important because it would mean that, you could enable FHE ZK rollups, and this would be needed for scalability. If your layer 1 is a homomorphic smart contract layer 1, you still would need some kind of ZK rollup strategy for scaling it, and therefore some ZK FHE rollup. And finally, a hardware acceleration, which is really what's going to bridge the gap of performance and make this practical in the next couple of years. All right. Thank you. Any questions?
Great talk, and very interesting applying FHE for privacy preserving smart contracts is an interesting approach. Any questions for Dan? Yeah, I think at the moment, I don't see any questions from the audience in the chat. So we have about 10 minutes left in the panel today. So let's get to the panel, and hopefully we have all the speakers with us. And feel free to discuss anything that you like. One thing I guess we could talk about that came up explicitly in Alex's presentation, and I think might also be relevant for other presentations, is the question of dynamic participation. Alex talked about it briefly at the end, and I think the question of dynamic participation also applies to like Ryan Stark when he mentioned threshold FHE and how validators would come together to decrypt the state in a threshold manner. The set of validators also changes, right? So maybe dynamic participation is also a relevant point there.
Yeah,
and maybe also with Pratyush's talk, the question of dynamic participation might also come when you're delegating proofs to a set of provers who are going to help you. Maybe it's possible for like people to join and leave. I don't know. So maybe it could be something that that the speakers could talk about.
Yeah, so actually this is interesting. So one of the main problems that isn't really solvable with crypto purely is how do you guarantee that a validator that's no longer a validator doesn't keep their share? And importantly, if that share is no longer valuable in terms of block rewards, what prevents them from just selling it to someone, right? So like how do you prevent validators from selling the shares that are no longer needed to someone who can then decrypt the previous transactions, right? I think that's a big problem, and I believe that a lot of threshold protocols will have the same problem. And right now, I think the best solution is either do the threshold stuff in SGX and then have a proof of erasure there, but then you're trusting hardware, so it's not necessarily what we want here. Or you basically need to have at least a blocking minority of validators, which are honest, so that nobody can reconstruct the 2/3 threshold by corrupting dishonest ones. But if someone has other ideas, I'd love to hear them, because this is really a problem that we have to figure out.
Yeah, I mean, frankly, it's probably a challenge for MPC-based solutions as well. I guess typically, at least when I think of these dynamic participation models for MPC, I think of the security as like, oh, someone participates for an hour and I need to trust them during that hour. But really, they do have the ability to do a lot of damage if they save their data and reveal it even, very far in the future.
Yeah, for delegation-based protocols, it's somewhat less of an issue in the sense that usually sort of these workers that you're delegating to are kind of ephemeral. So you don't really have to, they don't have any sort of long-term secrets. Of course, in the future, I mean, they can always store your witness that you seek to share with them and collude in the future. And they could always just publish it on like some random, public ledger. So you can't prevent that, but there's no sort of long-term state that is usually sort of needs to be shared between the current delegators and a future delegator. And in fact, in one of the sort of settings of our delegation scheme, you don't really, the workers don't even need to necessarily talk to each other. They're sort of, this is called the isolated setting. So basically, they only communicate with the delegator and not with each other. So this maybe further reduces issues of collusion and maybe dynamic participation. In particular, like you can always, because the workers are completely in some sense stateless, you can always just in the future pick a random different set of workers who are not talking with each other. So I think it's slightly less of a concern in the delegation setting.
I see. That's interesting. So in that particular case, when you have like stateless provers, does the delegator's work increase by a lot? How does that look like?
Yeah, so it does increase by a lot. So one example is you're using the delegator to act as sort of the trusted third party for implementing the multiplication functionality, right? So you could implement it via triples, and we have an implementation which uses the triples based multiplication between the workers to actually do the polynomial multiplication. But you can also just have the workers send their inputs for the multiplication gate back to the delegator, who does the fairly cheap act of just multiplying to finite field elements and resharing and sending back the results. The main overhead there actually just comes from the communication overhead between the delegator and the workers. So that's the main. There's the computational overhead is somewhat less of a concern there, but yeah, there it is more expensive than the scenario where the workers only talk to each other and perform all the computation with each other.
I'm sorry, Shashank, I need to actually leave because I have another call which is starting in 2 minutes. But thank you very much for having me. And if anybody wants to continue having a conversation, I'm very easy to find everywhere. Have a great day, everyone.
Thank you. Thank you so much. Yeah, and no worries at all. Yeah, in the last 2 minutes that we have left, maybe one question for Elette. The primitive that you have built, you've talked about how it could have applications to making passively secure MPC protocols actively secure, and you talked about one other application. So it certainly benefits MPC, and MPC could then benefit like things in the blockchain space. But do you see a more direct application to the blockchain setting?
Yeah, for sure. I think first of all, there's a lot that we haven't explored on this that probably people with more blockchain background should look at or jump on as well. But even just at a very fundamental level, and going back to some of the motivations that Alex had, that at any point, if I want to be able to prove to some collection of people about information that's split, then these are the sorts of techniques for this. So, you know, for example, okay, maybe this is not so much blockchain, but say, for example, I want to prove that I have some information, you know, I have a sufficient amount of money in my wallet, okay? And also some other information that's held by something else. Even just sort of this combination of the and of these different things where no individual person can verify this, but kind of collectively this information is split across the blockchain, for example, or across different agents there. Then these kinds of techniques can come in handy.
Right, cool.
I actually maybe have like a follow-up question if we have time.
Yeah, sure. Maybe a minute. Yeah.
Do you think that any notion of public verifiability makes sense for the kind of proof system that you guys define a lot? Like it has to be with respect to some kind of commitment scheme, I imagine, but I don't.
Yeah, so we haven't looked so explicitly in the commitment setting, but yes, I think so. I think, for example, really the property that we need about this split information is that there's some sort of linear combination. So, for example, if there is some public commitments to this information that have some sort of homomorphic linear properties, then indeed this could have potential for the public verifiability setting.
Gotcha.
Cool. So unfortunately, we are out of time. Thank you to all the speakers. I really enjoyed each and every talk today, and I would like to learn more about what you have done. So I'm going to spend some time offline on these papers. But really thankful that you could find some time to make it to the panel today. Yeah, thank you. Bye, everyone.